So as we were talking about the kidneys, I saw that you all drew me some good nephron drawings. So awesome job on those. And right now we're talking about the renal exchange process. So we're talking about filtration, reabsorption, secretion, and excretion. And we're going to talk about those happening in sort of different locations throughout the nephron as we go through today. So we really spent all of our last time on glomerular filtration, which is happening between the blood flow going past the nephron. So from the afferent arteriole going into the glomerulus to the efferent arteriole, and then filtration being the fluid moving out of the glomerulus into Bowman's capsule. We did some math regarding that, and we'll do a little more math today, but we were hopefully remembering that basically whenever we have movement across, sorry, not membranes, but across cells, across the endothelium and into a system. So just like when we're talking about capillaries, we have these starling forces that affect filtration. So we think about our hydrostatic pressure, which is the pressure of the fluid, like the pressure of the water itself from the plasma. And we also have oncotic pressure, which is like the pressure of proteins kind of pulling water towards them. So we went through the forces specific to the glomerulus. So we had our forces favoring filtration, which are the pressure of the blood going through the glomerulus, or the glomerular capillary hydrostatic pressure, same thing. And the pressure of the proteins in the filtrate in Bowman's capsule, of which there aren't too many, so it's kind of low, but favors filtration, the Bowman's capsule oncotic pressure. And then we had the reverse opposing filtration. Okay. And when we left off, we were really talking about regulation of the glomerular filtration rate. So we saw that, like, conceptually, when you raise pressure, when you raise arterial pressure, it means you're increasing blood flow. So as you increase blood flow, if more blood and more plasma goes through the glomerulus, more liquid is just naturally going to get filtered out. But we don't always want that to happen because blood pressure changes sometimes on like a minute-to-minute basis, right? Like it'll change in situations like when you're exercising or something momentarily, and you don't want to respond to that by then like peeing out all your water because that blood pressure can change and go back down after the event has happened. So we have a pretty wide range of arterial pressures, so 80 to 180, where we can keep that glomerular filtration rate constant. And the way that that happens is really through sort of three types of feedback. We have the feedback from smooth muscle, which contracts in response to stretching. So if it gets stretched by pressure, it's going to contract, increase that resistance, and therefore decrease the flow again. We have tubuloglomerular feedback, which is really hard to say, but it's just that there are some special cells in the ascending limb of the nephron loop. They're called macula densa cells, and they secrete these local factors called paracrine factors, that basically also tell the smooth muscle to contract. So that's going to have the same effect as the myogenic response. We also have mesangial cells. The mesangial cells are kind of sitting on the glomerulus itself. So they're not strictly smooth muscle, but they're also going to contract when we have higher pressure in the glomerulus. So they're going to restrict blood flow and therefore stop us from losing too much fluid due to a change in blood pressure. Okay, and then you drew a nephron. So we were on this sort of flow chart when we left off. So here what it's showing on both of these flow charts is that if we take our mean arterial pressure and it goes up, if it goes up for our cardiovascular system generally, that means that the pressure is going up in the afferent arteriole, which is the blood flow to the glomerulus. So without any type of regulation, what's happening kind of on one side here, this is showing what's happening without any type of feedback. So if the pressure in the afferent arteriole goes up, that means there's more blood flow going through the glomerulus. So there's higher capillary pressure in the glomerulus, which remember is one of our Starling's forces, right? So that's the glomerular capillary hydrostatic pressure. So we'd have higher pressure in the glomerulus. So that would tend to, because that hydrostatic pressure favors filtration. Sorry, was someone asking a question, or was that some other little sound? I don't see it. How do I open the chat here? Chat. Okay, no, sorry, that was some other ding then. Okay, so our Starling forces, one of them favoring filtration is the pressure in the glomerulus, that hydrostatic pressure. So if that hydrostatic pressure here goes up, which is the same thing as basically the blood pressure going up, that would increase our glomerular filtration rate because it's basically just pushing more plasma out. But we don't always want that to happen, so we have regulation. So here we see the regulation via the smooth muscle. So that high pressure stretches the smooth muscle, and the smooth muscle constricts in response. So that's this part. And then the constriction increases the resistance, which decreases the capillary pressure because it basically decreases the flow there. So this is negative feedback that will then lower the filtration pressure and lower the glomerular filtration rate. Now, our other regulation piece that's going to have the same effect to regulate that glomerular filtration rate, to bring it back down. Here we see on the right-hand side of our graph the effect of the paracrine factors from the macula densa. So this left-hand side is all the same as with our diagram that we just went through for the smooth muscle regulation. The difference is that we're showing all the way through. So if our glomerular filtration rate went up because blood pressure went up, that means the flow through that distal part of the nephron going past the macula densa would go up because we filtered more plasma out, so there's more filtrate going past the macula densa. And that increase in flow past the macula densa is what would cause those cells to secrete these paracrine factors, which are going to constrict the smooth muscles, which increases resistance, which decreases the glomerular capillary pressure. So that's just our other negative feedback loop. Okay. Those are both examples of intrinsic control, and the mesangial cells would kind of work the same way. So again, they just constrict down. But we also have extrinsic controls of our glomerular filtration rate. So because a decrease in blood pressure can decrease the glomerular filtration rate, we're also going to want to be able to control that. So part of what's going to control glomerular filtration rate is also going to have to do with like the nervous system. So here we have an example of blood pressure dropping due either to hemorrhage, so just to losing a bunch of blood, or to sweating, because if you sweat, your blood pressure is going to go way down if you're getting rid of a ton of liquid through the skin. Okay, so here we're starting out with the condition of losing plasma, basically, because you're either bleeding out or just losing fluid. And that's going to lower our venous pressure. Okay, so as we lower our venous pressure, so we know we have those like volume receptors, right? So volume and pressure receptors, the baroreceptors, are going to detect that change and they're going to respond. The way they're going to respond is that they're going to increase sympathetic activity. So increase the sympathetic nerves, like they're signaling, which is going to increase sympathetic nervous activity in the kidneys as well. So that's the renal sympathetic nervous activity. Now, the effect of an increase in sympathetic nervous activity on the kidneys is constriction of both the afferent and the efferent arterioles, which is going to increase the resistance of the blood flow around the nephron in the kidney. And that increase in resistance, just like in our previous diagrams, decreases the glomerular filtration rate, decreases urine flow, and decreases fluid loss. Now we have some other feedback loops here that we can see. So one thing is that as we decrease our fluid loss, that's going to bring the blood volume back up. So it's going to slowly sort of cancel out this flow. It's going to turn off this sympathetic nervous activity as we get back to normal. But another thing we can see is that we do have some effects happening because of what happens in the heart. So as our venous pressure goes down, this means that venous return to the heart is going down. And since we have less blood in the heart, we have lower cardiac output. So we have lower mean arterial pressure. So part of that goes into this flow with the baroreceptors. So that low mean arterial pressure is also ultimately increasing sympathetic nervous activity and increasing vasoconstriction. But we also have the direct effect of that mean arterial pressure, decreasing the glomerular filtration rate because there's less blood flowing through the glomerulus. And here we have this negative feedback loop from the vascular resistance in the kidneys, which is going to affect the mean arterial pressure because as we increase vascular resistance in the kidneys themselves, the kidneys are part of our sort of total peripheral systemic blood system. So they're going to increase our total peripheral resistance, which has the effect of increasing our mean arterial pressure. Okay. So here are some good examples of like practice essay questions. So I didn't write these, of course, they're always in your textbook, these checkpoint questions. But now that we're moving on towards essay exams, I would recommend that you practice responding to these. And actually, I'll write up my own sort of sample responses. So you guys use these as sort of little essay prompts, and I'll also write what I would write so that we can kind of start to practice how we would respond to a open question instead of just the multiple choice. So we'll save these for later. Yeah, and I'll give you some examples of what I think you should be saying. Okay, so what we talked about Monday and just now, the glomerular filtration, all of that stuff is happening right at the beginning of the nephron, right? So we don't actually want all that filtrate to be excreted from the body, right? We have 180 liters of plasma moving through there. That's way too much. We don't want to lose all our blood. So we have to think a lot about reabsorption. Reabsorption in the kidneys is going to be really important. So reabsorption is going to happen in the tubules, and we're going to have movement of solutes and water back into the paratubular capillaries. So the paratubular capillaries come back off that efferent arteriole and just wrap around the rest of the nephron so that we can have stuff moved from the filtrate back into the blood. Now, most of the reabsorption is going to occur in the proximal tubules. So the proximal tubules come like right after Bowman's capsule. And most of this is not going to be regulated. So we're not going to be thinking about these intrinsic and extrinsic factors much when we're thinking about what's happening in the paratubular capillaries. Now that won't be necessarily true when we get to other parts of the kidneys, but this first piece doesn't undergo much regulation. Okay. This is just a table of basically the amount of each of these things that's reabsorbed. So water is almost entirely reabsorbed. And we're going to see that our bicarbonate also largely being reabsorbed. Glucose should be, under normal conditions, 100% reabsorbed by the nephron. So all of these things are in the filtrate because everything comes out of the blood except for proteins. So none of these things are proteins, right? But we have our ions, we have water, we have glucose, we have urea coming out of the plasma and moving into that initial part of the nephron. But we really want a lot of that stuff to stay in the blood. Okay. So most of this is happening in the proximal convoluted tubules. And a little bit is happening in the distal convoluted tubules, and we'll distinguish that in the future. There's not a ton of a barrier for reabsorption here, and the proximal tubules in specific are really going to be specialized for reabsorption. So the cells that these molecules are going to have to move through are the epithelial cells of the tubules. So here we see the renal tubules, so the kidney tubules. They're going to have to go through the basement membrane, but that's not really hard for any of these molecules, so we're going to ignore it, and your book ignores it. Then they're going to go through the paratubular space, which is just diffusion, and they're going to move into the capillary endothelial cells. Now, the capillary endothelial cells are kind of spaced out, so they're not going to really block much of this. What's really going to control what is moving back into the blood is the epithelial cells in the tubules themselves. Okay, so just so that we make sure that we know where we are here, because we're about to zoom in. So here we can see a proximal convoluted tubule. We can see that there's some space, and we also have the capillaries around it. So the paratubule capillary here. And when we zoom in, what we're looking at here is the lumen of the renal tubule here. So the inside, actually, I think this picture is bigger over here. Yeah. Okay. So we've taken a cross section here. So we have the lumen of the tubule, or just the inside part of the tubule. This is where our filtrate is moving through. We have a membrane facing that called the apical membrane. So hopefully we remember way back when from our description of like anatomy of cells that an apical membrane is the part that faces the lumen, or kind of empty part of some area of the body. And on the opposite side, we have a basal part. So we have this basal part of the cell. We know it's basal because it's facing blood flow. Okay. So on the apical membrane of our, tubules here, we have these microvilli. So we can see that we're really increasing the surface area here for reabsorption. We can see that on the basolateral membrane, or really these lateral parts of these cells, we have these tight junctions. So we're kind of sealing off this space between the cells so stuff can't sneak through. And how tight exactly these junctions are going to be is going to differ depending on what part of the nephron we're in. So sometimes we're going to see some leakage here, and sometimes we're not. Yeah, okay. And the basement membrane. So these are the tubule epithelial cells. Okay. So reabsorption is mostly happening in these tubules, mostly in the proximal convoluted tubules. And really the most important thing that we're reabsorbing is the water. So we're reabsorbing a lot of different stuff, a lot of these different solutes. Glucose is really important that we're reabsorbing, but it's absolutely critical that we reabsorb the water, because otherwise we'd be losing 180 liters per day, which would absolutely kill you. Okay. You really only urinate about 1 to 2 liters of water as urine, and the only really necessary part of that 1 to 2 liters is 400 milliliters. So if you don't drink anything at all, in order to get rid of waste products in the blood, you will still urinate 400 milliliters. The rest of this is variation depending on how hydrated you are. So if you're well hydrated, I'm sure you've noticed you pee a lot more. When you're dehydrated, you don't. Okay. So 85% of this reabsorption of water is happening in the proximal tubules and the descending loop of Henle, so that first part of the loop of Henle. And this part is not regulated. So in the future, we'll see that some hormones regulate the other parts of reabsorption, but this first part doesn't really get affected. Okay. So here we have some examples of different ways things can be reabsorbed. So when I say it's not regulated, I don't mean that it doesn't take any energy. And I want to be clear about that. We're talking about kind of external effects because we are going to see active transport heavily involved in this process. Okay, but let's kind of go through this figure. So one thing that's important to note is when we're talking about the proximal tubules, so that first part of the nephron, we're not going to be changing the osmolality of the filtrate relative to the blood. So what I mean is that we're going to be reabsorbing both solutes and water. So we're not going to be like hyper concentrating the solutes in the blood or hyper concentrating them in the tubule. Although we will see that we're going to kind of strategically control solute concentrations in other parts of the kidney. Okay. So one thing that's happening as we're reabsorbing stuff is that sodium is actively transported out of the filtrate and into the peritubular blood. Okay. So we're going to have active transport of sodium, and some of this active transport of sodium is going to happen in a way that we've seen before. So back in A&P 1, we did some tracing of how sodium and potassium pumps really affect sodium concentrations and therefore can affect the transport of other molecules. So here we can see, this is just those same cells that we were talking about before. So here we see our apical membrane, our microvilli, so these swirls, increasing surface area. Here's our basal membrane. Here's our blood flow. Okay, so these cells are going to have sodium-potassium pumps on the basal side. So think here they're using red to show active transport. So like, let's pretend this is a sodium-potassium pump and that Y is sodium. So we're going to be actively pumping sodium out into the peritubular fluid here, which means we're going to end up with a low sodium concentration inside the cell, which is going to passively draw sodium from the filtrate into this cell. So that's a way that we can move sodium across this cell. And it would also create a high sodium concentration here in the peritubular fluid. And so then the movement of sodium from the peritubular fluid into the capillary would be passive because it goes down its gradient. One of the effects of this movement of sodium is that as we pump sodium basically all the way across this cell, so we take sodium and due to the action of this sodium-potassium pump, we're basically concentrating sodium here in this peritubular fluid. That sodium concentration, that high sodium concentration with its positive charges, is basically going to pull chloride ions with it. So the chloride ions are going to get pulled kind of all the way across. I don't think one of these specifically is chloride, but they would, if you think of a lot of sodium here, that negative chloride is going to get attracted to it here. Water is going to basically follow these solutes. So as we move a bunch of solutes into this space and are highly sort of concentrating these ions, that water via osmosis is going to kind of want to water down that concentration of the solutes. So it's going to flow into this area and into the capillaries as well. So basically all of this is kind of being controlled by this active transport of the sodium here in this example. And that's just all three of them at once. This is showing us just kind of a summary of what's happening here. So we had the filtration happening at Bowman's capsule, between the glomerulus and Bowman's capsule. We were removing a ton of fluid with a bunch of things dissolved in it via filtration. And now what we're talking about in the proximal tubules is reabsorption. So really important is that we're reabsorbing water. And the way we do that is by reabsorbing solutes, mainly through the active transport of sodium due to those sodium-potassium pumps on the basal membrane. chloride ions follow it, and then water follows that salt because it wants to like flow in and water down the salt. And so this whole process is isoosmotic because we had both the solutes and the water moving out of the filtrate. Okay. We're going to look in a second at, we're going to look at in a second at specifically glucose, because it's not just salt and water that are being transported. But one of the important things to think about as we start to think about glucose is this idea of a transport maximum. So the solutes and other molecules being reabsorbed are controlled by these carrier proteins, or these transport proteins, right? Proteins that go all the way across the cellular membrane and can carry them across. Now, we only have a certain number of these proteins. Like, we can express more of them, like we can make more of them sometimes, but there's going to be a certain number basically that we can fit, that we have on that basal membrane. And this means that at a certain point, they're going to get fully saturated. We're going to be reabsorbing as much of whatever solute it is that we can, because we're going to fill up those proteins. They're working as fast as they can. And when these proteins are fully saturated, we're going to call that the renal threshold. So the renal threshold is the maximum amount of that solute that we're going to be able to reabsorb. Okay. So glucose is an example of something that is normally 100% reabsorbed. So the renal threshold for glucose is above the normal concentration of glucose in the filtrate. So usually we're not going to hit that renal threshold. We're not going to fully saturate those carrier proteins, and all of the glucose is just going to go directly into the blood. But if we raise the levels in the filtrate of that solute, and here again, it's easier to just think of the example of glucose. So like if we raise glucose concentration in the filtrate, at a certain point, we're going to fully saturate the proteins that carry glucose from our tubular cells out into our capillary cells. And at this point, we're going to hit this threshold. And so some of the glucose would stay in the filtrate. And because it stays in the filtrate, it's then going to eventually show up in the urine when the urine gets excreted. Okay. So here's some of the specifics about glucose and its reabsorption. So the reason glucose is ending up in the filtrate in the first place is that the glomerulus, those cells, those fenestrated capillaries and the slit pores, they don't block glucose. So whatever the glucose concentration is in the plasma, it's going into the filtrate. And we talked about that, right? Like 125 milliliters of plasma are getting filtered out of the blood and into the glomerulus, into Bowman's capsule in a minute. And we also have 125 milligrams of glucose going with it. That was like one of our examples from Monday. And normally all of that is going to be reabsorbed in the proximal tubules. Nothing appears in the urine. And this is going to happen through secondary active transport at the apical membrane, and then facilitated diffusion at the basolateral membrane. So let's look at the example here. So here, instead of writing X and Y, helpfully, our book has labeled the actual solutes we're thinking about. So here we can see that we have our sodium-potassium pump on our basolateral membrane. So sodium moving out, potassium moving in. So sodium moving out means that we have this low concentration of sodium inside the tubule epithelial cell. And sodium in the filtrate is therefore attracted to this low concentration. So it moves from high concentration in the filtrate to low concentration in the cytoplasm of the tubule epithelial cells. And that concentration is kept low by this pump. Now, this is important for glucose because glucose moves in to the cell, basically using that same protein that's allowing this transport of sodium into the cell. So the transport of glucose into the cell is active because it's going against its gradient. There's not much glucose in this cell. There's more glucose in the filtrate, but it like hitches a ride with sodium. So we have secondary active transport transporting the glucose into our tubule epithelial cell. At that point, sorry, I think I referred to the glucose concentration wrong. We do have the high concentration because we're actively pumping it in. So then once we have this high concentration in the epithelial cell, it's able to diffuse into this space and eventually into our capillaries down its gradient using a carrier protein. So usually in the kidneys, what happens is that we have 100 milligrams per deciliter of plasma glucose. That's just the standard level. And usually our filtered load for glucose, so we remember that the filtered load is equal to the glomerular filtration rate times the concentration of our solute. Our usual filtered load for glucose is 125 milligrams per minute because their glomerular filtration rate is 125 milliliters per minute. Okay, so usually that's below our transport maximum for glucose because our transport maximum is 375 milligrams per minute. Okay. The theoretical renal threshold for glucose, so like the theoretical like amount of glucose that we could get across those carrier proteins is 300 milligrams per deciliter. I'm gonna share something in a second. But the actual renal threshold, so like this is how we would calculate it if every single carrier protein for glucose was able to be fully saturated, but that's not really reality. So the actual renal threshold for glucose is 160 to 180 milligrams per deciliter. This means that our filtered load is going to be 225 milligrams per deciliter. And I'm going to calculate all these out because that kind of feels like just a random amount of numbers. So how do I pull up a screen? I'm going to switch what I'm sharing. I'll share a whiteboard. Okay. So first, I'm going to show us how we calculate that theoretical. Oh, I can type. Awesome. Okay. How we would get that theoretical renal threshold. So theoretical renal threshold. Okay. So the way we get that theoretical renal threshold is we start, move this. Okay, maybe I can't move this. Okay. So we have our theoretical like maximum amount of glucose that we can move across, which is 300 milligrams per deciliter Okay. So we want to make sure that we are always working in the same units, and we have our glomerular filtration rate in milliliters per minute. So we have to do a conversion now. So we're going to multiply that by 1 deciliter per 100 milliliters. Okay. And then we're going to multiply that by our glomerular filtration rate. Per minute, which is how we get that value of 375 milligrams per minute as our theoretical renal threshold. Okay. Now, when we want to talk about our actual like filtered load of glucose, so filtered load is equal to our glomerular filtration rate by our concentration of our plasma concentration of whatever solute we're talking about. So in this case, glucose. It's P because we remember that we give concentrations by pressure sometimes. Okay, so we're gonna multiply our 125 milliliters per minute, which is our glomerular filtration rate. And then we have our actual renal threshold for glucose, which is between 160 and 180. So I'm going to put 180 here. So 180 milligrams per deciliter is actually the amount that those glucose transporters are going to be able to transport. And then we're going to convert those units again back to milliliters. So 1 deciliter is 100 milliliters. And if we multiply this all across, we're going to get 225. Okay. Save this. Okay. And that is our actual renal threshold for glucose. So it'd be slightly lower if you happen to be a person who has an actual renal threshold of 160 milligrams per deciliter for glucose. But that's where we're getting that number on, do I see questions? No, on the slide from. Okay. Okay. I'll have to show the whole thing. Settings. Okay. Okay. Sorry. I don't know why my screen sharing isn't going back. Okay, there we go. Okay, so that's where these numbers are coming from the renal handling of glucose. So this is our theoretical maximum load due to this theoretical renal threshold, which is what we calculated first. If we use this theoretical renal threshold of 300, multiply that by our glomerular filtration rate, we're going to get a maximum of 375 milligrams per minute of glucose being reabsorbed, but we don't have an actual renal threshold of 300 milligrams per deciliter because it's hard to really fully saturate those transport proteins. So the actual renal threshold is lower, like 160 to 180, which gives us a filtered load of glucose actually at about 225 milligrams per minute. So we can see that that's lower than our transport maximum if we were able to fill all those proteins. Okay. So we can also see this in graph form, basically. So here's our transport maximum that we calculated using that threshold of 300, right? Actually, I'll go through all these lines first. So first we can see the filtration of glucose. So we can see that as glucose in the blood increases, that just automatically increases the glucose in the filtrate. It's just going to keep going up and up. So that's because the glucose is free to move across the barrier between the glomerulus and Bowman's capsule, nothing's stopping it. So any increase in plasma glucose increases the concentration of glucose in the filtrate directly. To a certain extent, it also affects reabsorption. So under normal conditions, we have 100% of the glucose reabsorbed. Through that system we just looked at, through that active transport, the secondary active transport using sodium. So renal threshold starts here at about 160 to 180. So this is where we start to get saturation of those carrier proteins in the basolateral membrane. So they start to get kind of full. So we can see that our reabsorption rate is slowing down. And at a certain point, we're going to hit our transport maximum. So they're absolutely, absolutely all full. It cannot go any faster. So at that point, our rate of glucose movement like the amount of glucose being reabsorbed stops increasing, even though we increase glucose, because we just don't have any more proteins able to move glucose across the membrane. Now we can compare that to the amount of glucose that we'll see in the urine. So like if we increase glucose in your blood, for a long time, you're still not going to see any glucose in the urine, right? Because all of that glucose is getting reabsorbed. 100% of the glucose should be reabsorbed under normal conditions because we want that glucose, we want to use that glucose. But at a certain point, when we start to hit our renal threshold, when those carrier proteins are full up, we're going to start to see some of that glucose staying in the filtrate. Now, we don't want that to happen, but it's what happens just because of how many of those proteins we have in the basolateral membrane. So that's the point at which we're going to see glucose being excreted in the urine. And that's why one of the ways that we can, it's not like how we monitor glucose in the blood nowadays, but it's one of the reasons that the concentration of glucose in the urine can be an important indicator of things like diabetes, right? Because if we start to see glucose in the urine, we shouldn't normally. So that can indicate that we have a higher plasma concentration of glucose than this renal threshold. So we can tell that the kidneys can't work fast enough, basically, in order to reabsorb that much glucose. So your book says that people used to literally taste urine in order to determine whether someone had diabetes. That sounds crazy to me, but apparently it's true. Okay, I think this is a good place to stop, and we'll talk about secretion next. So secretion is mostly going to be happening in the more distal portions of the